imagine pulling back so far from Earth that the whole planet disappears. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Keep pulling back. The sun shrinks to a point of light. The Milky Way, our entire galaxy with its hundreds of billions of stars, becomes a faint smudge. Keep going. Millions of galaxies drift past you, each one a whole universe of suns. And then, at a scale almost too large to hold in your mind, something remarkable comes into view. The universe is not a random scatter of galaxies floating in empty darkness. It has a shape, a structure, a pattern so vast and so intricate that scientists have spent decades just learning how to see it. That structure has a name. We call it the cosmic web. The cosmic web is the largest known structure in the entire universe. It stretches across hundreds of millions of light years in every direction. A single light year is the distance light travels in one full year, moving at 186,000 miles every second. Now hold that thought and multiply it by hundreds of millions. The web is not a small thing. From far enough away, it looks like a glowing net. Long, thin threads of matter reach across the dark, connecting bright knots where galaxies cluster together. Between those threads, there are vast, dark, nearly empty regions called voids. The whole picture looks something like a sponge or a foam of soap bubbles, where the walls of the bubbles are made of galaxies, and the air inside the bubbles is almost nothing at all. Scientists sometimes describe the web as the skeleton of the universe. That is a good way to think about it. Just as your skeleton gives your body its shape, the cosmic web gives the universe its shape. Everything we can see, every galaxy, every star, every planet, every atom in your body sits somewhere along this enormous structure. The cosmic web spans the full reach of what we can observe. The observable universe, the part we can actually see with our telescopes, is about 93 billion light years across. And across that entire space, the web continues without a break. Scientists have found no edge to it, no place where the pattern stops and something else begins. As far as our best instruments can reach, the web goes on, What makes this so quietly astonishing is that the universe did not have to look this way. In the very first moments after the Big Bang, matter was spread almost perfectly smooth in every direction. There were only the tiniest differences, small ripples in density, some regions just barely more crowded with particles than others. But gravity is patient. Over hundreds of millions of years, those tiny differences grew. Denser regions pulled in more matter. Matter flowed toward those regions along paths that slowly became the filaments, the long glowing threads we see today. The web we observe now is the result of nearly 14 billion years of gravity doing its quiet, steady work. There is something deeply calming about that idea. The largest structure in the universe was not built in a flash. It grew slowly, the way a tree grows, the way a river carves a canyon, bit by bit, particle by particle. Gravity drew matter together into threads and walls and clusters, and the web took shape in the dark. When you look at images of the cosmic web, the ones produced by powerful computer simulations, or by mapping the positions of millions of real galaxies, the first thing most people feel is recognition. It looks familiar, even though nothing in everyday life comes close to its scale. It looks like the branching of neurons in the human brain. It looks like the network of rivers seen from high above. It looks like frost forming on a cold window. The universe, at its very largest scale, echoes patterns we find everywhere around us. Scientists are careful to say that these resemblances do not mean the web and a human brain work the same way. They do not. But the fact that similar patterns appear at such different scales, from the microscopic to the cosmic, hints at something worth sitting with quietly. The same simple rules, gravity pulling matter together, pressure pushing it apart, seem to produce similar shapes no matter where you look. Tonight, as you settle in, know that you are not floating in a formless dark. You are resting inside a structure, an enormous, ancient, glowing structure that stretches to the edge of everything we can see. And we are only just beginning to understand it. To understand the cosmic web, it helps to start at the very beginning. Not the beginning of the web itself, that comes later. The beginning of understanding what it actually is, in the simplest possible terms. The cosmic web is the large-scale structure of the entire universe. It is the way all matter, all galaxies, all gas and dust is arranged across the full span of space. If you could somehow zoom out far enough to see the whole observable universe at once, you would not see galaxies scattered randomly like salt thrown across a table. You would see them gathered into long, thin strands, into dense clumps, and around the edges of enormous empty bubbles. That arrangement, those strands and clumps and bubbles, is the web. The observable universe, the part we can actually see from Earth, stretches about 93 billion light years across. A light year is the distance light travels in one full year, moving at roughly 186,000 miles every single second. That is already a number too large to feel real. So think of it this way. If you shrank the sun down to the size of a grain of sand, the nearest star to our sun would still be about 4 miles away. And the observable universe, at that same scale, would be larger than the entire Earth. The cosmic web fills all of that space. The web is not young. It began forming very shortly after the Big Bang. The moment, roughly 13.8 billion years ago, when the universe itself began. In those first fractions of a second, the universe was unimaginably hot and dense, packed into a space far smaller than a single atom. Then it expanded rapidly and in all directions. As it cooled, tiny differences in density began to appear. Some regions had just a little more matter than others. Just a little. These small differences were the seeds of everything that followed. Gravity did the rest. Over hundreds of millions of years, regions with slightly more matter pulled in more matter from the space around them. The denser spots grew denser. The emptier spots grew emptier. Matter did not spread out evenly as the universe expanded. It clumped. It gathered. It stretched into long threads between the densest points. And slowly, over billions of years, the web took shape. Today, the web is made of several distinct parts. There are filaments, the long thread-like strands where galaxies cluster together. There are nodes, the bright, dense points where filaments cross, and where the largest collections of galaxies sit. And there are voids, the vast, nearly empty regions sit between the filaments like the spaces between the branches of a tree. Each of these parts will get its own time later. For now, just hold the picture in mind. Threads, knots, and empty spaces. That is the web. The filaments themselves can stretch for hundreds of millions of light years. Some of the largest known filaments span over 1 billion light years from end to end. To put that in perspective, our entire Milky Way galaxy, which contains somewhere between 100 billion and 400 billion stars, is only about 100,000 light years across. A single filament of the web could hold thousands of galaxies lined up along its length, and it would still stretch far beyond all of them. The matter in the web is not all the same kind. Some of it is the ordinary matter we know. The atoms that make up stars, planets, gas clouds, and everything we can see or touch. But scientists believe that most of the matter in the web is something else entirely. It is dark matter, a substance that does not emit light, does not reflect light, and cannot be seen directly. We know it exists because of the gravity it produces. Dark matter outweighs ordinary matter in the universe by roughly 5 to 1. The web, in a very real sense, is mostly made of something invisible. The gas that flows along the filaments is also largely invisible to ordinary telescopes. It is extremely thin and spread across enormous distances. In some filaments, scientists have detected this gas glowing faintly in ultraviolet light, a kind of light our eyes cannot see. Special instruments can pick it up, and when they do, they reveal the faint, ghostly glow of the web's own threads. All of this, the filaments, the dark matter, the glowing gas, the billions of galaxies, grew from those tiny, ancient differences in density, from almost nothing, from the faintest unevenness in the early universe. Something enormous and intricate slowly assembled itself. Gravity, patient and tireless, pulled it all into place over billions of years. And here it is, the largest thing that exists. The filaments are the longest structures in the universe. Each one stretches across hundreds of millions of light years. A single light year is already almost 6 trillion miles. So try to hold that in your mind. These threads span distances so vast that the the numbers stop feeling real. They become something closer to poetry than math. But they did not always exist. There was a time long ago when the universe held nothing like them. No filaments, no galaxies, no stars, just an ocean of hot, glowing gas spreading outward in every direction after the Big Bang. That gas was almost perfectly smooth. Almost. And that small word carries enormous weight. Scattered through that early gas were tiny variations in density. Some regions were just slightly thicker than others. The differences were incredibly small, perhaps 1 part in 100,000. That is like having a swimming pool where one tiny corner holds just a few extra drops of water. To any observer, it would look perfectly even. But gravity does not need much to work with. Gravity is patient. And over time, those faint differences began to matter. The slightly denser regions pulled in gas from the regions around them. As more gas gathered, the gravity grew stronger. Stronger gravity pulled in even more gas. The process fed itself slowly over millions and then billions of years. The denser spots grew denser still. The emptier spots grew emptier. The universe was sorting itself out, like sediment settling slowly to the bottom of a still pond. What formed first were not the filaments themselves, but something scientists call sheets or walls. These were broad, flat concentrations of matter, like enormous cosmic pancakes. Gas and dark matter gathered into these flat structures first, pulled by gravity along 2 directions at once. Then, along the edges where 2 sheets met, matter gathered even more tightly. Those meeting lines became the filaments. The threads of the cosmic web formed where flat sheets of matter intersected and collapsed inward together. This process has a name. Scientists call it the Zeldovich pancake model, after the Soviet physicist Yakov Zeldovich, who first described it mathematically in the 1970s. He predicted that matter would collapse first into flat sheets, then into filaments, then into the dense knots we now call galaxy clusters. Decades later, when telescopes became powerful enough to map the large-scale structure of the universe, they found almost exactly what he had described. The math had been right all along. The filaments themselves are not solid. They are not like rivers, or perhaps like the trails left by rivers after the water has thinned to almost nothing. They are made mostly of dark matter, that invisible substance that neither glows nor reflects. The dark matter forms a kind of skeleton, and ordinary matter, gas and dust, and eventually stars and galaxies, gathers along that skeleton the way moss grows along a fallen log. Gas flows along the filaments slowly, drifting toward the dense clusters at the intersections. As it travels, some of it cools and condenses. It falls into galaxies. Inside those galaxies, it collapses further into stars. The filaments, in this way, are not just structures. They are supply lines. They carry the raw material of stars across hundreds of millions of light years, feeding the galaxies that hang along their length like water droplets on a strand of silk. The whole process took an enormous amount of time. The first faint filamentary structures began to appear perhaps 1 billion years after the Big Bang. But the web we see today, with its full complexity and scale, took several billion more years to develop. The universe is roughly 13.8 billion years old. The web has been growing and shifting for most of that time. It is still growing now. There is something quietly remarkable about all of this. The largest structures in existence grew from the smallest possible differences. A tiny unevenness in a hot, ancient gas. A slight thickening here, a slight thinning there. Gravity noticed. Gravity remembered. And over billions of years, it turned those whisper-thin differences into threads that stretch across the observable universe. The filaments did not appear suddenly. They were not built. They grew the way a crystal grows in a cooling liquid, following rules written into the physics of the universe from the very beginning. Every thread you see in the cosmic web is the result of that long, slow, patient process. Each one carries the memory of those first tiny ripples in the early universe, stretched now across distances that take light hundreds of millions of years to cross. Between those long, bright threads of the cosmic web, there is something else entirely, something vast, something that at first seems like nothing at all. These are the voids. A void is exactly what the name suggests. It is a great, sweeping region of space where almost nothing lives. No bright galaxy clusters, no dense filaments, just a deep, dark, nearly empty stretch of the universe, curving away in all directions like the inside of an enormous bubble. Voids are not rare. They are not small. They fill most of the volume of the observable universe. When you look at a map of the cosmic web, the filaments and clusters catch the eye first. They are bright and complex, but the voids are the larger story. They take up roughly 80% of all the space the universe contains. Think about that for a moment. Most of the universe, by volume, is nearly empty. The largest known void is called the Boötes void, named after the constellation in whose direction it sits. It stretches roughly 330 million light years across. A single light year is already almost 6 trillion miles. The Boötes void contains that distance, multiplied by 330 million. If our entire Milky Way galaxy sat at the center of the Boötes void, the nearest neighboring galaxy cluster would still be impossibly far away. Astronomers discovered it in 1981, and for a time they struggled to explain it. A void that large seemed almost too empty to be real. But the voids are real, and they are not accidents. They formed the same way the filaments did, only in reverse. In the early universe, regions that were slightly less dense than average began to lose matter over time. Gravity pulled material away from those thin spots and toward the denser regions nearby. The filaments grew heavier. The voids grew emptier. It was a slow, steady draining, like water finding its way downhill over millions and millions of years. The matter that once filled these regions did not disappear. It moved. It gathered along the edges of the voids, building up the bright walls and filaments we see today. This means the voids and the filaments are not separate things. They shaped each other. The emptiness of a void is the direct result of the richness of the filaments around it. Every great thread of galaxies exists partly because a void beside it gave up its matter. They are two sides of the same slow process. The edges of voids are where things get interesting. Along those curved boundaries, where the void meets the surrounding web, galaxies do exist. They tend to be smaller and quieter than the galaxies found deep inside clusters. They are often younger in structure, less evolved, sitting at the rim of the emptiness like towns on the edge of a desert. Scientists call these void galaxies, and they behave differently from galaxies in denser regions. They have fewer neighbors. They experience less gravitational pressure. They evolve more slowly, more gently, shaped by a quieter environment. Inside the voids themselves, the darkness is not quite total. Scattered here and there, lone galaxies do exist, drifting through the near emptiness. They are rare. They are isolated, but they are there. Scientists believe some of these solitary galaxies were simply left behind as the void drained around them, too far from any filament to be pulled away. They sit in the deep quiet of the void, surrounded by almost nothing, with no neighbors for hundreds of millions of light years in any direction. It is one of the lonelier images the universe offers. The voids also play a role in something much larger. Scientists study them to understand dark energy, the mysterious force that is pushing the universe apart. As the universe expands, the voids expand with it. They grow larger over time. By measuring how voids change in size and shape across cosmic history, researchers can gather clues about how fast the universe is stretching and why. The emptiness, it turns out, is a measuring tool. The silence carries information. There is something worth sitting within all of this. The cosmic web is not just its bright parts. The light-filled filaments and the glittering clusters are only part of the picture. The voids are just as essential. They define the shape of everything around them. Without the empty spaces, there would be no structure at all. Just a uniform gray fog of matter spread evenly across space, with nothing to catch the eye, nothing to hold together, nothing to call a galaxy or a star or a world. The emptiness is not nothing. It is the space that gives the structure its shape. Where the voids end, something remarkable begins. At the edges of those vast empty spaces, the filaments meet. Long threads of gas and dark matter reach toward one another across hundreds of millions of light years. And where several filaments converge, where they cross and tangle and press together, something extraordinary forms. A galaxy cluster, the largest gravitationally bound structures in the known universe. Think of the cosmic web as a net. The filaments are the cords, and the knots, the places where the cords tie together. Those are the galaxy clusters. They are the brightest, most crowded, most energetic places in the entire web. A typical galaxy cluster holds anywhere from hundreds to thousands of individual galaxies, all bound together by gravity. Our own Milky Way is a large galaxy containing hundreds of billions of stars. Now, imagine 1,000 galaxies like that, or more, all gathered into one enormous region of space. That is a galaxy cluster. The scale is almost too large to hold in the mind. The nearest major cluster to our own galaxy group is the Virgo cluster, sitting about 65 million light-years away. It contains more than 1,300 galaxies. The whole thing spans roughly 8 million light-years across. And yet, in the context of the full cosmic web, the Virgo cluster is a modest, mid-sized knot. Gravity is the force that builds these clusters and holds them together. Over billions of years, gravity pulled matter toward the densest regions of space. Gas and dark matter and galaxies all drifted slowly inward, drawn toward the same points where the filaments crossed. The process was not quick. It took most of the age of the universe to build the clusters we see today. But gravity is not the only force at work inside a cluster. The space between the galaxies is not empty. It is filled with an extremely hot, thin gas called the intracluster medium. This gas glows in X-rays, a form of light invisible to human eyes, but detectable by space telescopes. The gas reaches temperatures of tens of millions of degrees, sometimes even hundreds of millions of degrees. It is some of the hottest ordinary matter anywhere in the universe. That heat comes from the same gravity that built the cluster. As gas fell inward over billions of years, it accelerated. It collided with other gas. Those collisions converted the energy of motion into heat. The cluster, in a sense, warmed itself through its own construction. This hot gas exerts pressure outward, pushing against the inward pull of gravity. The two forces, gravity pulling in and gas pressure pushing out, reach a kind of slow, steady balance. Scientists call this state hydrostatic equilibrium, which simply means the cluster is not collapsing further and not flying apart. It is holding its shape, a vast, hot, glowing structure suspended in space by the balance of opposing forces. Magnetic fields also thread through galaxy clusters, though they are far weaker than the magnetic field around Earth. These fields shape how the hot gas moves and how particles travel through the cluster. They are subtle, but they leave their mark on the structure over long stretches of time. Then there are the galaxies themselves, moving through the cluster like slow ships crossing a dark sea. They do not sit still. They orbit the cluster's center, pulled by the combined gravity of all the other galaxies, all that hot gas, and the enormous halo of dark matter that surrounds and permeates the whole structure. The galaxies interact with each other as they pass. Sometimes their gravity pulls long streams of stars out of one another. Sometimes two galaxies merge entirely, forming a single, larger galaxy. The cluster is not a static place. It is always in motion, always changing, always reshaping itself across timescales of billions of years. The most massive clusters in the universe act as gravitational lenses. Their gravity is so strong that it bends the light coming from galaxies far behind them. That light curves around the cluster like water bending around a stone. Astronomers can see this effect as arcs and rings of distorted light in telescope images. It is one of the most direct ways scientists measure how much mass a cluster actually contains, including the dark matter that cannot be seen directly. All of these forces, gravity, gas pressure, heat, magnetic fields, the slow drift of galaxies, work together inside every cluster. Each one pushes or pulls or shapes the structure in some way. None of them acts alone. The cluster is the result of all of them at once, operating across billions of years in a region of space where the threads of the cosmic web have chosen to meet. Dark matter is the reason any of this exists at all. Without it, the cosmic web would never have formed. The filaments would not stretch between galaxies. The clusters would not have gathered. The voids would not have opened up. Everything you have heard about so far, every thread, every node, every great empty space was shaped first by something we cannot see, cannot touch, and cannot measure directly. We only know it is there because of what it does. Scientists call it dark matter. It is not dark the way a shadow is dark. It does not block light. It does not absorb light. It simply does not interact with light at all. Radio waves, visible light, X-rays, they all pass straight through dark matter, as if it were not there. The only force dark matter responds to is gravity, and that turns out to be enough to build a universe. Here is how much of it there is. For every 1 kilogram of ordinary matter, the kind that makes up stars, planets, gas clouds, and you, there are roughly 5 kilograms of dark matter. About 85% of all the matter in the universe is dark matter. The atoms that make up everything we have ever seen or touched or measured are actually the minority. The universe is mostly made of something we have never directly detected. That number takes a moment to settle in. Imagine filling a room with 6 buckets of sand. 5 of those buckets are dark matter. Only 1 bucket is everything else. Every star, every planet, every ocean, every living thing, every atom in the periodic table, all of human history, all of recorded science, all of the light we have ever seen from the sky. That is the 1 bucket. The rest of the room belongs to something invisible. Dark matter does not clump together the way ordinary matter does. It does not form stars or planets. It spreads out in enormous, diffuse clouds called halos, wide, roughly spherical regions of invisible mass that surround and envelop galaxies and galaxy clusters. The Milky Way sits inside one of these halos right now. Our entire galaxy, with its hundreds of billions of stars, is wrapped in a cloud of dark matter that extends far beyond the visible edge of the galaxy itself. The halo of the Milky Way stretches outward for roughly 600,000 light years in every direction. The visible disk of stars we call the Milky Way is only about 100,000 light years across. The dark matter halo is 6 times wider than the galaxy it holds. Think of it this way. If the visible Milky Way were the size of a dinner plate, the dark matter halo surrounding it would be the size of a dining room table. The plate sits in the middle. The table is what holds it in place. These halos were the first structures to form after the Big Bang. Long before the first stars ignited, dark matter was already gathering. It pulled together under its own gravity, slowly building up dense regions and thin connecting bridges between them. Ordinary matter, the gas that would eventually become stars, simply fell into the shapes that dark matter had already made. The filaments we see today trace the paths where dark matter gathered first. The clusters sit where dark matter halos grew the largest. The voids exist where dark matter was sparse, and ordinary matter had nothing to fall toward. Dark matter did not build the cosmic web the way a spider spins silk, deliberately and from a single point. It built the web the way frost forms on a cold window, slowly, quietly, following invisible patterns written into the early universe, spreading outward from countless points at once until the whole structure appeared. Scientists have mapped the distribution of dark matter across large regions of the sky using a technique called gravitational lensing. The same bending of light that galaxy clusters produce by measuring how background galaxies appear slightly distorted and stretched. Astronomers can work backward to figure out where the invisible mass must be sitting. The maps they produce look almost identical to the maps of the cosmic web itself. The dark matter and the visible structure follow the same pattern. They are the same structure, seen two different ways. One is the skeleton. The other is the flesh that grew around it. Every galaxy you have ever seen in a photograph, every glowing spiral arm, every bright cluster of young blue stars, every ancient elliptical galaxy glowing soft and gold. All of it sits inside a dark matter halo. All of it was guided there by gravity that came from something invisible. The web of light that astronomers photograph is real. But underneath it, holding it all in place, is a web of darkness far older and far larger than anything we can see. For a long time, we could only guess at the shape of all this. We knew galaxies existed. We knew they clustered together. But the full picture, the vast web of filaments and voids stretching across hundreds of millions of light years, that picture was hidden from us. Mapping it required patience, technology, and a kind of quiet determination took decades to build. The first real glimpse came in 1989. A team of astronomers named Margaret Geller and John Huckra had spent years collecting something called redshifts. A redshift is a small shift in the color of a galaxy's light that tells you how fast it is moving away from us. Because the universe is expanding, the farther away a galaxy sits, the faster it moves away, and the more its light shifts toward the red end of the color spectrum. By measuring thousands of these redshifts, Geller and Huckra could calculate how far away each galaxy was. Distance plus direction gave them position, and position, plotted carefully on a map, gave them structure. What they found stopped the scientific world cold. The galaxies were not scattered randomly through space. They were arranged in long curved sheets and thin threads, with enormous empty regions between them. The map looked like a slice through a sponge, or perhaps the cross-section of a soap bubble. The team called one of the most striking features the Great Wall, a sheet of galaxies stretching across more than 500 million light-years of space. It was, at the time, the largest known structure in the universe. The cosmic web had been seen for the first time. That first map was a thin slice, like cutting through an orange and looking at just one flat cross-section. It covered only a narrow band of the sky, but it was enough to show the pattern. The universe was not smooth. It was not random. It had texture, and that texture had a shape, and that shape was the web. Over the following decades, astronomers built bigger surveys. The 2DF Galaxy Redshift Survey, completed in the early 2000s, mapped the positions of nearly 250,000 galaxies across a wide stretch of sky. If you could look at that map from far away, you would see something that looks almost like a living thing. Long, pale threads curve and intersect. Bright knots sit where the threads cross. Between them, the great dark voids open up like rooms with no walls. The whole image glows faintly, the way a city looks from an airplane at night, with light concentrated along roads and clustered at intersections, and deep darkness spreading between. Then came the Sloan Digital Sky Survey, which pushed even further. It mapped more than 1 million galaxies in fine detail. Astronomers could now see the web just as a rough outline, but as a detailed structure with real texture. The filaments had width, the clusters had shape, the voids had boundaries. The map covered such a large portion of the sky that scientists could begin to measure the web's repeating patterns. The way the spacing between clusters follows a regular rhythm set down in the early universe. Looking at these maps feels like looking at something ancient and alive. The filaments glow pale silver white in the visualizations, built from the combined light of millions of galaxies, too distant to see individually. The voids are a deep, soft black, not the sharp black of empty space, but something gentler, like the space between stars on a clear night. The clusters where filaments meet blaze bright, dense concentrations of light that mark the busiest crossroads in the universe. What makes these maps remarkable is not just what they show, but how they were made. Every single data point in those surveys is a real galaxy, a real place. Each one contains hundreds of billions of stars. Each one likely holds countless planets. And yet, on the scale of these maps, each galaxy is just a single faint dot, a pixel in a picture so large that the human mind can barely hold it. The map is made of worlds, and the worlds together draw a shape that no single world could ever see on its own. Jeller and Hukra could not have known, when they began collecting those first redshifts one by one, that they were drawing the outline of the largest structure the universe contains. They were simply measuring light, carefully and patiently, the way all good science is done. And the light, gathered together, revealed something that had been there all along, waiting quietly in the dark, enormous and intricate and real. There is a kind of light that has been traveling toward us for almost 14 billion years. It did not come from a star. It did not come from a galaxy. It came from the universe itself, from a time so early that stars had not yet formed, when everything that exists was packed into a space smaller than the Milky Way. That light is still here. It surrounds us on all sides, right now, faint and cool and ancient. Scientists call it the cosmic microwave background, and it is the oldest light we can ever hope to see. To understand what it is, picture the universe as a very young, very hot place, in its first could not travel freely. Particles of light kept bumping into other particles, scattering in all directions, trapped in a glowing fog. The whole universe was like the inside of a star, bright and opaque, with no clear path for light to take. Then, around 380,000 years after the Big Bang, something changed. The universe cooled just enough for electrons and protons to join together and form the first hydrogen atoms. The fog lifted. Light was suddenly free to travel, and it has been traveling ever since. That moment of release is called recombination, the point when matter and light finally separated. The light that escaped in that instant has been streaming outward for nearly 14 billion years. As the universe expanded, that light stretched and cooled. It started as a fierce, hot glow. Today it has cooled to just under 3 degrees above absolute zero, the coldest temperature possible. It now falls in the microwave range, invisible to human eyes, but detectable by sensitive instruments in space. When scientists point those instruments in any direction, they find this ancient light waiting there, a soft, even glow that fills the entire sky. What makes this light so extraordinary is that it is not perfectly smooth. It has tiny variations, small patches that are ever so slightly warmer or cooler than the average. The differences are incredibly small, just a few 100,000ths of a degree. But those tiny differences carry enormous meaning. The slightly warmer patches mark places where matter was just a little more concentrated in that ancient fog. The slightly cooler patches mark places where matter was just a little more spread out. Those small differences in density, those gentle ripples in the early universe, are the seeds from which everything grew. The regions that were slightly denser pulled in more matter over time. Gravity is patient. Over hundreds of millions of years, those denser patches attracted gas, and the gas collapsed into the first stars and galaxies. The slightly emptier regions stayed empty, growing into the vast voids we see today. The pattern of warm and cool patches in the cosmic microwave background is, in a very real sense, a baby picture of the cosmic web, the structure that Geller and Huckra traced with their galaxy surveys, the filaments and clusters and voids that stretch stretch across billions of light years. All of it was already written in that ancient light, in the form of those tiny temperature shifts, before a single star had ever burned. 2 missions gave us our clearest views of this ancient light. The first was NASA's WMAP satellite, which mapped the full sky between 2001 and 2010 and produced a detailed picture of those temperature variations. The second was the European Space Agency's Planck satellite, which completed an even finer map between 2009 and 2013. The Planck map is one of the most precise measurements in the history of science. It shows the seeds of the cosmic web with stunning clarity, a modeled pattern of warm and cool patches spread across the entire sky like a faint, ancient fingerprint. Scientists can take that fingerprint and, using the known laws of physics, predict what the universe should look like today. They can calculate where the filaments should form, where the clusters should gather, where the voids should open up. And when they compare those predictions to the actual surveys of galaxies, the match is remarkable. The web we see in the distribution of galaxies today reflects the pattern that was already present in the universe's first light, the oldest thing we can observe, and the largest structure we can map are telling the same story, separated by almost 14 billion years of time. There is something very still about that idea. The universe left a record of its earliest moments written in light, and that light is still here, still carrying its message, still surrounding us on all sides. We live inside the echo of the beginning, and that echo, read carefully, shows us the shape of everything that came after. That echo shaped everything, and one of the most striking shapes it created is something astronomers call a supercluster. A supercluster is a vast collection of galaxy clusters and galaxy groups all bound together in one enormous region of space. Think of it this way. A single galaxy holds hundreds of billions of stars. A galaxy cluster holds hundreds of galaxies. A supercluster holds dozens of those clusters, all gathered in the same broad neighborhood of the cosmic web. They are the largest gravitationally influenced structures we know of, stretching across hundreds of millions of light years. Our own home sits inside one. The Milky Way a supercluster called Laniakea. In the Hawaiian language, Laniakea means immeasurable heaven. Scientists only mapped its full shape in 2014, and what they found was breathtaking. Laniakea spans roughly 520 million light-years across. It contains the mass of about 100 million billion suns, and it holds more than 100,000 galaxies, including our own. For most of human history, we had no idea we lived inside something so vast. We knew our galaxy. We knew our local group of galaxies. We knew the Virgo cluster nearby. But the full shape of Laniakea, that sweeping, flower-like structure with long arms reaching inward toward a central point, only became visible when scientists mapped the motion of galaxies rather than just their positions. That motion is part of what makes superclusters so fascinating. Galaxies inside a supercluster are not sitting still. They flow. Scientists tracked the movement of thousands of galaxies and found that they all drift very slowly toward a central region called the Great Attractor. The Great Attractor sits at the heart of Laniakea like a deep, slow drain, pulling everything in its neighborhood toward it. The Milky Way itself is moving in that direction right now, drawn by a gravitational pull so large it is difficult to fully picture. This is the rhythm of the supercluster, not a fast pulse, not a sharp beat, but a long, slow inward breath that takes billions of years to complete. Everything drifts. Everything flows. The galaxies of Laniakea are moving toward each other across distances so vast that the motion is invisible to us in a single human lifetime. But it is real, and it is constant. Laniakea is not alone. The universe contains many superclusters. The Coma supercluster, the Perseus-Pisces supercluster, the Shapley supercluster, which is one of the most massive concentrations of galaxies in the known universe. The Shapley supercluster sits about 650 million light-years away and contains so much mass that it tugs on our entire local region of space, adding its pull to the Great Attractor's influence. We are caught between enormous gravitational forces, drifting slowly through a web of giants. Each supercluster sits at the intersection of filaments, those long threads of gas and galaxies that connect the web. Picture a city built where several highways meet. The filaments are the highways. The supercluster is the city. Matter traveled along those threads for billions of years, pooling at the crossings, building up mass, drawing in more galaxies, growing denser and more complex over time. The web did not just create superclusters. It fed them slowly and steadily across the entire age of the universe. And yet, despite their size, superclusters are not permanent in the way we might imagine. Dark energy, the force that drives the universe's expansion, is slowly pulling everything apart. Over vast stretches of future time, the outer edges of superclusters will lose their connection to the center. Galaxies on the fringes will drift away, carried by the expansion of space itself. What is loosely bound today will eventually come undone. The slow inward breath of the supercluster will, in the far future, be overcome by an even slower outward push. So there is a cycle here, even at this enormous scale. Matter gathers, structures form, gravity pulls inward. Then, over timescales almost too large to hold in the mind, expansion wins. The rhythm is long and quiet, but it is there. Laniakia will not last forever. Neither will the Shapley supercluster, or the coma, or any of the others. They are grand and ancient, but they are also temporary, like everything in the universe. They formed from the seeds planted in the first moments of time, grew along the threads of the cosmic web, and will one day dissolve back into the expanding dark. For now, though, they are here, enormous, slow, and full of light. And we are here too, inside one of them, small and quiet, carried gently along in the drift. Gravity is the oldest force in the story of the cosmic web. It was there at the very beginning, pulling the first wisps of matter together in the dark, and it has never stopped working. Quietly, steadily, across distances so vast they barely seem real. Gravity weaves the web together, thread by thread, cluster by cluster, over billions of years. Think of gravity not as a sudden force, but as a patient one. It does not rush. It simply pulls and waits and pulls again. Over time, even the faintest tug adds up. A small clump of matter draws in a little more matter. That slightly larger clump draws in still more. The process builds on itself, slowly and without pause. Scientists call this gravitational collapse, and it is the engine behind almost every large structure in the universe. In the early universe, matter was spread out almost evenly across space. Almost, but not quite. There were tiny differences, regions that were just slightly denser than the space around them. Those tiny differences were enough. Gravity began pulling on those denser patches, drawing nearby matter inward. Over hundreds of millions of years, those small clumps grew into the first galaxies. The galaxies gathered into groups. The groups gathered into clusters. And the clusters arranged themselves along the long, glowing filaments of the cosmic web. What is remarkable is how gravity works across such different scales all at once. Inside a single galaxy, gravity holds stars in orbit around a central core. Between galaxies in a cluster, gravity binds them into a shared neighborhood. And at the largest scales, gravity pulls entire clusters toward one another along the filaments. The same force that keeps your feet on the ground is also, very slowly, drawing the Milky Way toward the Great Attractor. A massive concentration of matter roughly 250 million light-years away. The pull is real. The motion is real. We are drifting toward it right now, carried along at hundreds of kilometers per second, though we feel nothing at all. The filaments themselves are shaped by this gravitational dance between neighbors. A filament forms where two large voids press against each other, and matter flows along the boundary between them. Gravity pulls that matter inward toward the densest points along the filament, the nodes, where galaxy clusters sit like bright knots in a net. The filament is not a solid structure. It is more like a slow river of gas, dust, and galaxies, all flowing gently toward those bright gathering points. Everything along the filament leans inward, nudged by gravity from both sides. This is what makes the cosmic web feel alive in a quiet way. Nothing sits still. Every galaxy is moving. Every cluster is pulling on its neighbors. The whole structure is in constant, slow motion. A vast gravitational conversation happening across billions of light years. Astronomers can measure these motions. They call the large-scale flow of galaxies toward dense regions peculiar velocity, meaning the motion caused by gravity on top of the general expansion of space. By mapping these flows, scientists can trace the invisible shape of the web, even in regions too faint to see directly. Gravity also explains why the web has the structure it does, why there are filaments and voids rather than a smooth, even spread of galaxies. Computer simulations that model gravity acting on the early universe produce webs that look almost identical to the one we observe. The filaments, the clusters, the great empty voids, all of it emerges naturally from gravity alone, working on the tiny density differences left over from the first moments after the Big Bang. The web is not random. It is the inevitable result of gravity doing what gravity always does. There is something deeply calming about that. The universe did not need a complicated plan to build something so intricate. It only needed one simple rule: matter attracts matter. Given enough time, that single rule produced everything: galaxies, clusters, filaments, superclusters, the whole shining structure stretching across the observable universe. The web is gravity made visible, written in light across the dark. And every part of it is connected to every other part. The Milky Way is not floating freely in empty space. It is embedded in a filament, which connects to a cluster, which connects to a supercluster, which leans toward other superclusters along threads of matter hundreds of millions of light years long. We are not separate from the web. We are woven into it, held by the same quiet force that shaped everything around us. Gravity does not distinguish between a falling apple and a falling galaxy. It simply pulls gently and without end, and in doing so, holds the whole universe together. The filaments of the cosmic web are not empty threads. They are filled with gas and dust, stretched thin across unimaginable distances, carrying the raw material that galaxies need to grow. This gas is not like the air around us. It is plasma, which means it is so hot that its atoms have been torn apart into loose clouds of charged particles. And the temperatures inside these filaments are some of the most extreme anywhere in the known universe. The gas that fills the filaments exists in a state scientists call the warm-hot intergalactic medium. That is a long phrase, but the idea is simple. It is gas that sits between galaxies, spread across the filaments at temperatures ranging from 100,000 degrees to 10 million degrees. 10 million degrees. That is nearly twice as hot as the visible surface of the sun. And yet this gas glows so faintly that for decades, astronomers could barely detect it at all. This warm, hot gas is thought to hold a significant portion of all the ordinary matter in the universe. For a long time, scientists added up all the matter they could see in stars and galaxies, and the numbers did not match their predictions. There was matter missing. Not dark matter, which is a separate mystery, but ordinary matter made of protons and neutrons, the same stuff as you and everything around you. The warm, hot gas hiding in the filaments appears to be where much of that missing matter was hiding all along. It was there the whole time, invisible, stretched thin across the web. The coldest places in the cosmic web tell a different story. Deep inside the densest parts of filaments, where gas begins to fall toward forming galaxies, pockets of cold gas collect. These clouds can drop to temperatures just a few degrees above absolute zero, which is the coldest anything in the universe can possibly get. Absolute zero is roughly minus 273 degrees Celsius. Some of the gas clouds drifting along the outer edges of filaments come remarkably close to that limit. Hot and cold exist side by side across the web, separated by vast distances, but part of the same flowing structure. The dust in the filaments is just as remarkable as the gas. Cosmic dust is not like household dust. It is made of tiny grains of carbon, silica, and ice, each one smaller than a human hair. These grains were forged inside dying stars and blown outward into space when those stars exploded. Over billions of years, the dust spread through the filaments, riding the slow currents of gas. When that dust eventually falls into a forming galaxy and collapses into new stars, it becomes part of planets, atmospheres, and eventually living things. The dust in the filaments is ancient stardust in transit, moving slowly toward its next purpose. Some filaments carry shocks, which are waves of energy that travel through the gas, slow, invisible pressure wave. When two filaments meet at a galaxy cluster, or when a galaxy moves at high speed through the surrounding gas, it creates a shock wave. These shocks heat the gas to extraordinary temperatures and can stretch for tens of millions of light years. They are among the largest single structures of energy anywhere in the observable universe. And they move through the web so slowly that a human lifetime would not be long enough to notice any change at all. The gas in the filaments also carries a faint magnetic field. Scientists have detected these fields threading through the cosmic web, stretched incredibly thin, but present across hundreds of millions of light years. How these magnetic fields formed is still an open question. They may have originated in the very early universe, before the first stars ever lit up. They may have been seeded by the first galaxies, and then stretched outward along the filaments over billions of years. Either way, the web is not just made of matter and gravity. It carries magnetism too, woven through the gas like an invisible current running through a wire. All of this, the scorching plasma, the near-frozen gas clouds, the ancient dust, the slow shock waves, the faint magnetic fields, exists in the spaces between galaxies, in the thin threads that hold the web together. None of it is visible to the naked eye. None of it can be seen on a clear night from a dark field. But it is there, surrounding every galaxy, threading through every filament, connecting every part of the universe to every other part. The web is not just a structure of light and gravity. It is a living system of gas and energy, constantly moving, constantly feeding, constantly changing, even as it looks from the outside perfectly still. And yet, even as the web feeds and breathes and carries its invisible currents, something else is at work, something quieter, something that operates not on the scale of a single filament or a single galaxy cluster, but on the scale of everything at once. That something is dark energy. Dark energy is a name scientists gave to a force, or perhaps a property of space itself, that causes the universe to expand. Not just to expand, but to expand faster and faster over time. Right now, as you listen to this, every part of the cosmic web is being pulled away from every other part, filaments are not breaking. The clusters are not dissolving. But the vast, empty voids between them are growing. Space itself is stretching, and dark energy is the reason why. Scientists first discovered this acceleration in 1998. Two separate teams of astronomers were studying distant exploding stars called supernovae. These explosions are useful because they always burn at roughly the same brightness. That makes them like measuring sticks across the universe. When both teams looked at their data, they found the same surprising result. The distant supernovae were fainter than expected. They were farther away than they should have been. The universe was not just expanding, it was speeding up. Both teams won the Nobel Prize in Physics in 2011 for that discovery. Nobody knows exactly what dark energy is. Scientists believe it makes up roughly 68% of everything in the universe. Ordinary matter, the kind that makes up stars and planets and people, accounts for only about 5%. Dark matter, the invisible scaffolding of the web, makes up around 27%. Dark energy dwarfs them both. It is the dominant ingredient of the cosmos, and we still do not fully understand it. One way to think about dark energy is to imagine space as a fabric. Gravity pulls pieces of that fabric together. Dark energy pushes the fabric outward in all directions at once. On small scales, gravity wins. That is why galaxies hold together. That is why clusters hold together. Gravity is strong enough at close range to resist the outward push, but on the very largest scales, across hundreds of millions or billions of light years, dark energy wins. The web stretches, the voids grow wider. The filaments, though they remain intact, grow longer and thinner as the space around them expands. This stretching has a quiet, subtle effect on the web structure. Scientists have found that the largest voids in the universe are slowly growing larger. Not because matter is leaving them, but because the space inside them is expanding faster than gravity can pull it back. A void that measured 300 million light years across a billion years ago may measure 400 million light years across today. The numbers are almost too large to hold in the mind, but the process is gentle and the cosmological constant, a term Albert Einstein introduced into his equations of general relativity over a century ago. He originally added it as a kind of balancing force, a way to keep his model of the universe from collapsing under its own gravity. He later called it his greatest mistake because he thought the universe was static, and it turned out not to be. But when astronomers discovered dark energy, they realized Einstein's constant might not have been a mistake at all. It may have been an early glimpse of something real. The math fits. The cosmological constant, as a description of dark energy, still holds up today. What dark energy means for the cosmic web in the very long run is a kind of slow, quiet isolation. Galaxies that are gravitationally bound to each other, like the Milky Way and its neighbors in the local group, will stay together. Gravity will hold them close, but the clusters beyond our local neighborhood are already moving away from us. In tens of billions of years, scientists believe they will have moved so far that no light from them will ever reach us again. The web will still exist, but its most distant parts will become unreachable, invisible, gone beyond any possible horizon. For now, though, the web remains whole. The filaments still connect. The clusters still glow. The gas still flows. Dark energy stretches the space between things slowly and without sound, the way a tide pulls at the shore without ever announcing itself. It is one of the quietest forces in the universe, and it shapes everything. To understand the cosmic web, humans first had to build something that had never existed before. Not a telescope, not a rocket, a mind made of mathematics running inside a machine. For most of human history, the night sky was something you could only watch. You could count the stars. You could trace the shapes of galaxies with careful eyes and patient hands. But the cosmic web is too large to see all at once. No single telescope can hold it. No photograph can capture it whole. To truly understand it, scientists needed a way to run the universe forward in time, from the very beginning, and watch what happened. That idea, building a working model of the universe inside a computer, began to take shape in the 1970s and 1980s. Early simulations were simple by today's standards. They few thousand particles of matter, each one standing in for a vast region of space. The computers were slow, the models were rough, but even those early, blurry pictures showed something remarkable. The matter did not spread out evenly. It clumped, it stretched into threads, it left great empty spaces behind. The web was there, even in those first crude attempts to see it. One of the most important early steps came from a group of scientists working in the 1980s on what they called N-body simulations. The N stands for number, and the idea is straightforward. You place a large number of particles in a virtual space. You give each one a tiny gravitational pull. Then you let the simulation run step by step and watch as gravity does its slow, patient work. The particles drift toward each other. They form clumps. The clumps grow. Filaments appear between them. Voids open up in the spaces left behind. What emerged from those early simulations looked, with striking accuracy, like what astronomers were beginning to see in real sky surveys of the time. The match between the simulations and the real universe was not perfect at first. Scientists argued about the details. They debated how much dark matter there was and what kind. They tested different starting conditions, different rules, different assumptions about how the early universe behaved. Each new simulation taught them something. Each failure pointed toward a better question. Science, at its best, works exactly this way. By the 1990s, computers had grown powerful enough to track millions of particles at once. The simulations grew sharper. The web inside them grew more detailed. And then, in 2005, a team of researchers released something that changed the field entirely. It was called the Millennium Simulation. It modeled more than 10 billion particles of dark matter, moving through a cube of virtual space, nearly 2 billion light years across. It ran on a supercomputer in Germany, and it took weeks to complete. When the results appeared, the images were breathtaking. Filaments stretched across the virtual sky in glowing threads. Clusters blazed at their intersections. Voids opened like dark rooms between the glowing walls. It looked almost exactly like the real universe, as seen in the deepest sky surveys ever taken. What made the Millennium Simulation so powerful powerful was not just its size. It was what scientists could do with it. They could zoom in. They could watch individual galaxies form inside the filaments. They could trace the flow of gas along the threads. They could test ideas about how stars are born, how black holes grow, how the web changes over billions of years. The simulation became a kind of laboratory, a place to run experiments that no telescope could ever perform. Since then, the simulations have only grown larger and more detailed. Projects like Illustris, Eagle, and the TNG simulations, short for Illustris TNG, have added gas, radiation, magnetic fields, and the feedback from exploding stars into their models. Each new generation captures more of the universe's true complexity. Each one brings the virtual web closer to the real one. What is quietly astonishing about all of this is how well it works. Scientists began with a handful of basic rules. Gravity pulls dark matter clumps. The universe expands. They fed those rules into a machine, and out came something that looks, in its broad shape and fine detail, like the actual universe we live in. The same filaments, the same voids, the same glowing clusters at the crossroads of it all. The universe, it seems, follows rules that are deep and consistent. And when humans finally found the right tools to listen, the universe repeated itself faithfully. Inside a machine, in a room, on a pale blue planet, tucked inside one small corner of the very web it was trying to understand. That pale blue planet has a name, of course, and the small corner it occupies has a name too. We call it the Milky Way, and for most of human history, we assumed it sat somewhere ordinary in the universe, somewhere average, somewhere in the middle of things. The truth, as it turns out, is far stranger and more interesting than that. Our galaxy sits inside a structure called the Laniakea Supercluster. Laniakea is a Hawaiian word meaning immeasurable heaven. Scientists gave it that name in 2014 when a team led by astronomer Brent Tully finally mapped the full shape of our cosmic neighborhood. What they found was enormous. Laniakea stretches roughly 520 million light years across. It contains the mass of about 100 million billion suns, and the Milky Way sits near its outer edge, is one of the quiet surprises of modern astronomy. We are not at the heart of our supercluster. We live on the outskirts, close to a long, curving filament that feeds into a much denser region far away. That denser region is called the Great Attractor, a point of enormous gravitational pull deep inside Laniakea. Everything in our supercluster, including the Milky Way, is slowly drifting toward it. We are moving at roughly 600 kilometers per second in that direction. We cannot feel it. We cannot see it directly. But the motion is real, and it has been measured. For a long time, the Great Attractor was one of the great mysteries in astronomy. Scientists could tell that something was pulling our galaxy and thousands of others toward a single point. But a dense band of dust and stars in our own galaxy blocked the view. The Milky Way itself was hiding the answer. Only in recent decades, using radio waves and infrared light that can pass through that dust, did astronomers finally peer behind the curtain. What they found was a massive concentration of galaxies called the Norma Cluster, sitting at the center of that gravitational pull. It is not a single object. It is a whole city of galaxies, dense and bright, drawing the surrounding universe slowly inward. There is something quietly humbling about this. Our galaxy, with its hundreds of billions of stars, is itself just one small piece of a much larger flow. We are downstream in a river of gravity we can barely see. The Milky Way also sits surprisingly close to the edge of a large void. A void is a vast region of space with very few galaxies inside it. The one near us is called the local void, and it stretches for hundreds of millions of light years in the direction of the constellation sculptor. Voids push outward because there is so little matter inside them. Their gravity is weak, and the surrounding regions of denser matter pull away from them over time. The local void is actually pushing the Milky Way, nudging it gently away from empty space and toward the denser structures of Laniakea. So our galaxy is being pulled from one direction and pushed from another, caught between a void and an attractor, drifting through the web in a path set by forces that stretch across hundreds of millions of light years. Scientists find this deeply interesting motion through the web is not random. It is shaped by the large-scale structure around it. The filaments, the voids, the clusters, all of it influences where our galaxy goes and how fast it moves. We are embedded in the web, not just sitting beside it. There is one more surprise worth resting with. The Milky Way, for all its size, is not especially remarkable by cosmic standards. There are galaxies in the web far larger, far brighter, far more massive. The Andromeda Galaxy, our nearest large neighbor, is actually bigger than the Milky Way. The two galaxies are moving toward each other and will eventually merge billions of years from now into a single larger galaxy. That future galaxy already has an informal name among astronomers. They call it Milkomeda. It will still be just one small node in the web, one faint light among countless others, sitting at the edge of a supercluster, drifting toward a distant attractor, surrounded on one side by the quiet dark of a void. The universe does not place us at the center of anything, and yet somehow that makes our position feel more remarkable, not less. We are here in this specific place, at this specific moment, on the outer edge of an immeasurable heaven, watching the whole slow structure move around us. The filaments of the cosmic web are not just bridges between galaxies. They are rivers, and like rivers on Earth, they carry something precious along their length. They carry the raw material that galaxies need to grow. Gas flows through the filaments. Enormous clouds of hydrogen and helium, the two simplest elements in the universe, drift slowly along these vast threads. Gravity pulls the gas toward the denser regions, the places where filaments cross, where galaxy clusters sit waiting. And as that gas travels, it feeds the galaxies it encounters along the way. This process has a name. Scientists call it cold accretion, which means the slow, steady feeding of a galaxy by cool streams of gas flowing in from outside. The gas does not crash in all at once. It threads its way in, like water soaking into dry earth. It arrives gently over millions and millions of years, and when it arrives, it gives the galaxy new material to work with. New gas means new stars can form. New stars mean new light, new heat, new planetary systems. Think about what that means. A galaxy sitting along a filament is not isolated. It is connected to an enormous supply line stretching across hundreds of millions of light years. The filament feeds it. The galaxy grows. Stars are born inside it. Some of those stars will have planets. Some of those planets may have oceans, atmospheres, the conditions for something extraordinary. All of that begins with gas, moving slowly along a thread of the cosmic web. Galaxies that sit near the dense nodes of the web, those busy crossroads where multiple filaments meet, tend to be older and more massive. They have been fed longer. They have consumed more gas over their lifetimes. The largest galaxies in the universe, giant elliptical galaxies that can hold trillions of stars, almost always sit at the hearts of galaxy clusters. They grew large precisely because they sat at the richest intersections, where the most gas arrived from the most directions. Galaxies out in the voids, far from any filament, tend to be smaller and quieter. They have fewer neighbors. Less gas reaches them. They form fewer new stars. They are dimmer, slower, more isolated. The web does not treat all galaxies equally. Where you sit in the web shapes what you become. This is one of the most striking things about the cosmic web. It is not just a structure. It is a system of nourishment. The filaments are the veins, and the gas is the blood, and the galaxies are the organs that depend on what flows through them. Everything is connected to everything else by these slow, invisible streams, and the connection runs even deeper than that. When a massive star reaches the end of its life, it explodes. That explosion, called a supernova, blasts heavy elements out into space. Elements like carbon, oxygen, iron, and calcium. These elements travel outward from the dying star and mix into the surrounding gas. That enriched gas eventually joins the larger flow along the filaments. It drifts toward other galaxies. It becomes part of new star systems. The atoms forged in one dying star can end up inside a planet, orbiting a star in a completely different galaxy. The web carries not just hydrogen and helium. It carries the products of every star that has ever lived and died. The filaments are threaded with the ashes of ancient suns. There is something else worth holding onto. The gas that flows along the filaments is not silent. It emits a faint glow of ultraviolet light, a soft shimmer that scientists have only recently learned to detect. For decades, the filaments were mapped mostly by the galaxies they contained. The gas itself was nearly invisible, but newer telescopes built to detect this faint emission have begun to reveal the filaments directly. Scientists can now watch the gas glowing softly in the dark between galaxies, tracing the shape of threads that were once only theoretical. The web is becoming visible in ways it never was before. And what scientists see confirms what the simulations predicted. The gas is there. It flows. It feeds. The filaments are alive with slow, quiet movement. Our own Milky Way has been fed this way. The gas that formed our sun, the gas that became Earth, the oceans, the air, the carbon in every living thing. All of it arrived here through some ancient channel of the web. We are downstream from something vast. We are the result of a flow that began long before our solar system existed, carried here along threads of gas and gravity, stretching back to the earliest ages of the universe. And yet, for all the richness of those filaments, the spaces between them tell their own quiet story. The great voids of the cosmic web look empty at first glance. They are the dark regions, the vast hollows that sit between the filaments and clusters like the spaces between the threads of a net. When astronomers first mapped them, the voids seemed like absences, places where nothing happened, places the universe had simply skipped over. But science has a way of finding life in the places that look lifeless. Voids are not truly empty. Inside them, scattered thinly across hundreds of millions of light years, there are galaxies. Not many, not the dense crowds you find along the filaments or packed into clusters, but they are there, drifting alone in the dark, separated from their neighbors by distances almost too large to imagine. These are called void galaxies, and they are among the most isolated objects in the known universe. A galaxy living deep inside a void might have no significant neighbor for tens of millions of light years in every direction. These lonely galaxies tend to look different from the ones that live along the filaments. They are often smaller. They tend to be bluer in color, which tells astronomers that they are still actively forming new stars. Galaxies in crowded regions often run out of fresh gas over time, their star formation slowing and eventually stopping. But void galaxies, left undisturbed by the gravitational pulls and collisions that reshape galaxies in denser regions, seem to hold onto their gas longer. They keep building. Slowly, quietly, they continue to grow in the dark. This is one of the ways the cosmic web is always changing. Not just in the filaments, where gas flows and galaxies merge, but in the voids, where isolated galaxies evolve along their own separate path. The web is not a static picture. It is a slow process, always in motion, always shifting. The voids themselves are growing. As dark energy pushes the universe to expand faster and faster, the voids stretch wider. The filaments that border them are being pulled apart at their edges. Matter that once sat near the boundary of a void gets drawn further into the filaments and clusters, leaving the interior of the void even emptier than before. The voids are hollowing out over time, becoming more defined, more extreme. What was once a slightly underdense region billions of years ago has become a vast, sweeping hollow today. Scientists have measured this. The largest known void in the observable universe is called the Boötes Void, named for the constellation in the direction where it sits. It stretches roughly 330 million light-years across. That number is hard to hold in the mind. Our entire Milky Way galaxy is only about 100,000 light-years wide. The Boötes Void could swallow thousands of galaxies the size of ours and still have room. When astronomers first discovered it in 1981, some were so surprised by its size that they struggled to explain how such a large, empty region could have formed in the time the universe has existed. Even inside the Boötes Void, there are a handful of galaxies, 60 or so, scattered across that enormous space. They are not truly alone in the absolute sense, but they are as close to alone as anything in the observable universe gets. There is something quietly moving about that image. A small galaxy drifting through a void hundreds of millions of light-years wide. No nearby neighbors, no filaments feeding it fresh streams of gas. Just slow, patient evolution in the dark. Stars forming one by one. Planets perhaps forming around some of those stars. And somewhere on one of those planets, perhaps, something looking up. The voids are also not perfectly smooth on the inside. Even within them, there are faint traces of structure, tiny filaments, thinner and more delicate than the great threads of the web, thread their way through the void interiors. They are ghostly, barely there, but they suggest that the web's organizing force reaches even into the emptiest places. Gravity does not stop at the edge of a void. It simply works more slowly, more gently, with less material to shape. This is the nature of the universe at its largest scale. Nothing is ever completely finished. Nothing is ever completely still. The filaments are feeding. The clusters are growing. The voids are widening. And inside those widening voids, small galaxies drift and build and change, following their own quiet arc through time. The web is not a fixed thing. It is a process. It has been changing since the first moments after the universe began, and it will keep changing long after every star we can see today has gone dark. Light is the great messenger. It carries the story of everything it has touched across any distance, across any amount of time. And when we look out at the cosmic web, we are not just seeing space. We are seeing time itself, laid out before us like a long, slow river stretching back toward the beginning of everything. This is one of the quietest and most astonishing things about the universe. Light travels fast, but the universe is vast. So the light reaching our telescopes tonight left its source long ago. When we look at a galaxy 1 billion light years away, we see it as it was 1 billion years ago. We are not seeing the present. We are seeing the past. The farther we look, the further back in time we see. This means the cosmic web is also a time machine. Every layer of depth in the sky is a different era of the universe's life. Nearby galaxies show us the web as it looks today, or close to it. Distant galaxies show us the web as it was when the universe was young. And the farthest objects we can detect, the ones near the edge of the observable universe, show us the web in its earliest, most fragile form. In those early images, the web looks different. It is rougher, less organized. The great filaments are thinner and less defined. The clusters at the nodes are smaller, still gathering mass. The voids are shallower, not yet fully carved out by the slow pressure of dark energy. It is like looking at a photograph of a forest when the trees were still saplings. You can see the shape of what it will become, but it has not arrived there yet. As we move forward in time, closer to the present, the web grows more structured. The filaments thicken. The clusters grow denser and brighter. The voids deepen and widen. This change happens across billions of years, far too slowly for any living thing to watch in real time. But light preserves every stage. Each distance in the sky holds a different chapter of the same long story. The light that travels along the filaments carries something else too. As it moves through the gas and dust that threads the web, it changes slightly. Some wavelengths, some colors of light get absorbed by the gas. Others pass through. Scientists study these tiny changes in the light's color to learn what the filaments are made of, how dense they are, how hot they are, and how they have changed over time. It is a kind of reading done with spectrographs, instruments that split light into its component colors, the way a prism splits sunlight into a rainbow. This technique has revealed something remarkable. The gas in the filaments today is not the same as the gas in the filaments billions of years ago. Early on, the gas was almost entirely hydrogen and helium, the two lightest elements, born in the first minutes after the Big Bang. Over time, stars formed inside the galaxies along the filaments. Those stars lived and died. They forged heavier elements in their cores and scattered them outward when they exploded. That enriched gas drifted back into the filaments. The filaments today carry traces of carbon, oxygen, and other elements that did not exist in the early universe. The web has been slowly enriched by every star that ever lived inside it. There is a particular kind of light that astronomers use to trace the web across deep time. It is called the Lyman alpha line, a specific wavelength of ultraviolet light emitted by hydrogen gas when it is energized. Hydrogen is the most common element in the universe, and it glows in this specific color when starlight or other radiation excites it. By looking for this glow, scientists can map where the hydrogen gas is, which means they can trace the filaments even in the very distant, very early universe. The Lyman alpha line has become one of the most powerful tools for reading the web's history across time. And so, the light does what it has always done. It carries the record forward. Every photon that reaches our instruments has traveled an almost unimaginable distance, threading through filaments, skirting the edges of voids, passing through the halos of galaxies. It arrives carrying the memory of where it has been. We catch it, split it into its colors, and read what it has to say. The web across deep time is not a single image. It is a sequence, a slow unfolding caught in light. From the thin, rough threads of the early universe to the thick, glowing filaments of today, the story is written in every wavelength we can detect. We only have to look and listen with the right instruments, and the light will tell us everything. The universe is not silent. That might seem like a strange thing to say. Space is a vacuum, after all. Sound needs something to travel through, air or water or solid ground, and most of space has none of those things. But silence and stillness are not the same. The cosmic web vibrates, it pulses, and scientists have found ways to hear it. The trick is translation. Just as we can take the light from a distant star and split it into colors to read its chemistry, we can take other kinds of signals and convert them into sound. Radio waves, pressure waves, the faint oscillations locked inside ancient light. All of it can be shifted into frequencies our ears can detect. When scientists do this, the universe stops being a picture and becomes something closer to music. One of the most remarkable examples comes from the cosmic microwave background, that faint glow of ancient light left over from the early universe. In the first moments after the Big Bang, the young universe was a dense, hot soup of particles and energy. Sound waves, real pressure waves, moved through this soup like ripples through water. They compressed gas in some places and stretched it thin in others. These compressions and expansions left a pattern in the cosmic microwave background, a pattern of slightly warmer and slightly cooler spots. Scientists have taken this pattern and converted it into audio. The result is a deep, low rumble, a sound that dropped in pitch as the universe expanded. It is the oldest sound in existence. It is the voice of the universe as an infant. These ancient sound waves did not just fade away. They left a physical mark on the universe that we can still measure today. Astronomers call this the baryon acoustic oscillation, which means the rhythmic bouncing of ordinary matter, driven by those early pressure waves. The preferred distance between galaxy clusters today, roughly 500 million light years, reflects the size of those ancient sound waves, frozen in place when the universe cooled. The cosmic web itself carries the memory of that first great vibration. The spacing of its nodes, the distance between the dense clusters where filaments meet, echoes a sound that rang out nearly 14 billion years ago. Closer to home, scientists have detected something similar in the behavior of galaxy clusters. When two massive clusters collide, they send pressure waves outward through the hot gas that fills the space between galaxies. These waves are enormous, far larger than any structure on Earth, but they behave like sound waves in a medium. Instruments on X-ray telescopes have captured these ripples as faint rings of slightly different temperature moving outward from the collision site. Converted to audio, they produce a deep, resonant hum far below what human ears can hear without being shifted upward in pitch. But the vibration is real. The sun also sings. Pressure waves move through the sun's interior, making its surface rise and fall by tiny amounts, sometimes just a few kilometers across a body more than 1,000,000 kilometers wide. Scientists study these oscillations to understand what the sun looks like on the inside, a field called heliosysmology, which means using sound to see inside a star. The same technique applied to distant stars has revealed their ages, their compositions, and the size of their cores. Sound, it turns out, is one of the best tools we have for seeing through things we cannot directly observe. Even the filaments of the cosmic web may carry their own kind of vibration. Simulations suggest that gas flowing along filaments does not move in a perfectly smooth stream. tumbles and churns, creating turbulence, which is a kind of disordered, swirling motion. This turbulence generates pressure fluctuations that, in a medium dense enough to carry them, would behave like sound. The filaments are too thin and too spread out for these waves to travel far. But the motion is there, written in the behavior of the gas, detectable by instruments sensitive enough to catch the subtle shifts in temperature and density. What all of this tells us is that the cosmic web is not a frozen sculpture. It moves. It breathes. It carries the imprint of forces that acted on it billions of years ago, and it responds to forces acting on it right now. The ancient rumble of the Big Bang shaped where the filaments grew. The slow pull of gravity keeps them growing still, and somewhere inside all of that motion, there is a kind of rhythm, not a melody exactly, but a deep, patient cadence that runs through everything. We built instruments to catch the light. Then we learned to listen too. And the universe, it turns out, has been speaking all along. There is something quietly astonishing waiting for you in the mathematics of the cosmic web. It is not complicated. It does not require equations or years of study to feel its weight. It only requires that you look at two things side by side and let your eyes do the work. Place an image of the cosmic web next to an image of a human brain. The filaments of galaxies and the branching networks of neurons look almost identical. Long, thin threads. Bright nodes where the threads meet. Dark, open spaces between them. The resemblance is so striking that scientists have studied it carefully, measuring the structures with the same tools they use to compare any two physical systems. In 2020, a team of researchers published a study comparing the cosmic web to the network of neurons in the human cerebral cortex. The cortex is the outer layer of the brain, the wrinkled surface where much of our thinking happens. What they found was remarkable. Both systems have roughly similar complexity in how their nodes connect. Both have similar fractions of their total volume filled by active structure versus empty space. The cosmic web is about 77% void. The brain's cortex is about 77% water. The numbers are not perfectly matched, but they are close enough to stop you in your tracks. is not a sign that the universe is conscious, or that the brain somehow mirrors the cosmos on purpose. What it tells us is something more interesting than that. It tells us that certain mathematical rules produce similar-looking structures across wildly different scales. The same geometry that organizes galaxies across hundreds of millions of light years also organizes the cells inside your skull. The universe runs on a small set of elegant rules, and those rules show up everywhere. One of those rules involves branching networks. When gravity pulls matter together over long distances, it tends to form webs rather than clumps. Thin threads connect denser nodes. The same pattern appears in river systems, where small streams feed into larger rivers, which feed into even larger ones. It appears in the veins of a leaf, where tiny channels carry water from the stem out to the edges. It appears in the blood vessels of your body, branching from the heart outward in a pattern that covers every corner of your tissue. Mathematicians call these branching structures fractal-like, meaning they repeat similar patterns at different scales. The cosmic web is not a perfect fractal, but it shares this quality of self-similarity, where the general shape of the structure looks roughly the same whether you zoom in or zoom out across a certain range of scales. Clusters of galaxies connect to superclusters. Superclusters connect to the filaments. The filaments connect across distances so vast that light takes hundreds of millions of years to cross them, and yet the underlying geometry echoes something you can hold in your hand, something you can see in the branching of a tree or the spreading of frost across a cold window. There is a ratio that appears often in nature called the power law. It describes how the number of objects of a certain size relates to the number of objects of a different size. In the cosmic web, the distribution of galaxy clusters follows a power law. Smaller clusters are far more common than larger ones, and the relationship between their sizes follows a clean, predictable curve. The same kind of curve describes the distribution of earthquakes, the sizes of craters on the moon, and the frequency of words in any human language. The universe seems to favor this particular mathematical shape again and again. What all of this suggests is that the cosmos is not random. It is structured. It follows rules that are simple at their core, even when the results look impossibly complex. A handful of forces, gravity chief among them, working over billions of years, produce structures that echo across every scale we know how to measure. There is something deeply calming in that idea. The same patient arithmetic that placed the Milky Way inside its filament also placed the neurons inside your brain. The same tendency toward networks and nodes and branching threads runs through the largest structure in the universe. And through the most complex structure we have ever found inside it, you are not separate from the web. You are made of the same matter that flows along its filaments, shaped by the same rules that shaped the filaments themselves. The universe did not just produce you. In some quiet, mathematical sense, it produced you in its own image. And that image, it turns out, looks like a web of light stretched across the dark. And yet, for all its quiet order, the cosmic web is not a peaceful place. The web looks still from a distance. Filaments hang like threads of light between the dark. Clusters glow at their crossings like bright knots. But inside those clusters, something slow and enormous is always happening. Galaxy clusters are colliding. They have been colliding for billions of years, and they will keep colliding for billions more. When two galaxy clusters meet, the event is the largest collision in the known universe. Not the largest explosion, not the largest impact, the largest collision of any kind anywhere that we have ever observed. Two clusters can each contain hundreds or even thousands of galaxies. Each cluster carries vast clouds of hot gas. Each one is wrapped in a massive halo of dark matter. When they meet, all of that comes together in a slow, grinding, billion-year crash. The galaxies themselves almost never hit each other directly. Space inside a cluster is still enormous, and the galaxies are small compared to the distances between them. They pass through each other's space like two swarms of fireflies moving through the same field. But the hot gas that fills each cluster does collide. It slams together at millions of miles per hour. It heats up to temperatures of hundreds of millions of degrees. It glows in X-ray light, the kind of light our eyes cannot see, but our telescopes can. That glowing stretches out in long, torn shapes between the merging clusters, like something being slowly pulled apart. One of the most famous examples of this is called the Bullet Cluster. It sits about 3.7 billion light-years away from Earth. Scientists observed it after two clusters had already passed through each other. The hot gas had been slowed and separated by the collision, but the dark matter, which does not interact with gas the way normal matter does, had passed straight through. The dark matter halos of each cluster kept moving, pulling the galaxies with them. This left the hot gas behind in the middle, and the galaxies and dark matter ahead on either side. Scientists could map the dark matter by watching how its gravity bent the light of more distant galaxies behind it. The result was one of the clearest pieces of evidence we have ever gathered that dark matter is real. A collision produced the proof. This is the fragile balance the web holds. Every cluster at every node is in motion. Every filament is feeding new matter into those nodes. Every collision reshapes the structure slightly. The web is not frozen. It breathes slowly, over timescales we can barely imagine. What makes this balance so remarkable is how many things have to be exactly right for any of it to work. The ratio of dark matter to normal matter in the universe sits at roughly 5:1. If that ratio were very different, clusters would form differently. Filaments would be thinner or thicker. The web would look nothing like what we see. The conditions that produced the web we live inside required the universe to begin with a very specific set of ingredients in very specific amounts, distributed in a very specific way. The temperature of the early universe had to fall at just the right rate for matter to clump together at all. The strength of gravity had to be precisely what it is. Dark energy had to be present in just the right amount to stretch space without tearing the filaments apart before they could form. Adjust any one of these by even a small amount, and the web as we know it does not exist. The clusters do not form. The galaxies do not gather. The stars inside them do not ignite. The planets around those stars do not cool. The conditions for life do not arise. It is a chain of precision that stretches from the first fraction of a second after the universe began all the way to this moment. moving slowly in and out of your lungs. The collisions are violent. The scales are incomprehensible. And yet the system holds together. Clusters merge and grow larger. The web thickens at its nodes. New filaments form as matter continues to flow. The slow violence of colliding clusters is not destruction. It is construction. Each collision produces a larger, more massive structure than existed before. The web does not break under the force of its own collisions. It grows from them. There is something almost reassuring in that. The universe absorbs its own violence and turns it into structure. It takes the chaos of two enormous clusters grinding together and produces, over billions of years, something more organized than what came before. And yet, for all we have learned about the cosmic web, some of the deepest questions remain open. The web is not just a map of where galaxies live. It is also a map of the universe itself, its shape, its geometry, its ultimate nature. And that map still holds secrets we have not yet read. One of the oldest and strangest questions in all of science is this: what shape is the universe? Not the shape of a galaxy or a cluster or even a supercluster. The shape of everything. The total shape of all space and time. Scientists have spent decades trying to answer this, and the cosmic web is one of their most powerful tools for doing so. The universe could be flat. Not flat like a piece of paper, but flat in a geometric sense, meaning that parallel lines never meet and never spread apart. They simply go on forever, side by side, without curving. Current evidence strongly suggests the universe is very close to flat. The cosmic web, spread across billions of light years, shows no signs of large-scale curving. The filaments stretch in straight lines. The voids are round, not warped. This is a clue, though not yet a final answer. The universe could also be curved, like the surface of a sphere, where two lines that start out parallel will eventually meet. Or it could curve the other way, like a saddle, where parallel lines slowly spread apart. Each of these shapes would leave a different fingerprint on the cosmic web. The spacing of the filaments, the sizes of the voids, the way clusters are distributed across the sky. All of these carry information about the geometry of space itself. Scientists measure these patterns carefully, looking for any sign that the web bends in ways that would reveal a curved universe. So far, the web looks flat, but the measurements are not yet precise enough to be certain. There is still a small window of uncertainty, and inside that window, the true shape of the universe remains unknown. There is another mystery the web points toward, one even harder to solve. The web has a pattern. Filaments and voids repeat across the sky in a way that is not random. This pattern has a preferred scale, a distance at which clusters tend to cluster, a spacing that shows up again and again across billions of light years. Scientists call this the baryon acoustic oscillation scale, which simply means the echo of ancient sound waves that moved through the early universe before the first stars ever formed. Those sound waves left a faint rhythm in the distribution of matter, and the cosmic web still carries that rhythm today, like a song playing so slowly. It takes billions of years to hear a single note. By measuring this rhythm carefully, scientists can use the web as a kind of cosmic ruler. They can measure how fast the universe is expanding at different points in its history. And when they do, something strange appears. Different methods of measuring the expansion rate give slightly different answers. The number you get from studying the cosmic microwave background, that ancient glow from the early universe, does not quite match the number you get from studying the web and the galaxies within it. This disagreement is small, but it is real, and it has not gone away. Scientists call it the Hubble tension, named after Edwin Hubble, the astronomer who first showed that the universe was expanding. The tension suggests that something in our understanding is incomplete. Perhaps dark energy behaves differently than we think. Perhaps there is a new kind of particle we have not yet detected. Perhaps the early universe contained something that our current models do not account for. The web holds another open question close to its heart. We know the web is built on a skeleton of dark matter. We know dark matter exists because of how it bends light and pulls on galaxies. But we do not know what dark matter actually is. No experiment has ever directly detected a dark matter particle. The web is is the largest structure in the universe, and its bones are made of something we cannot name. These are not failures. They are invitations. Every gap in our knowledge is a door that has not yet been opened. The cosmic web, this vast and ancient structure, is still teaching us. Each new telescope, each new survey, each new map of the sky adds detail to a picture that grows more beautiful the more clearly we see it. We are not at the end of understanding. We are somewhere near the beginning, and there is something quietly wonderful about that. The universe is still full of questions, and we are still here asking them. The cosmic web has existed for nearly 14 billion years. It grew slowly, quietly, from tiny ripples in the early universe. Gravity pulled gas and dark matter together. Filaments formed. Clusters gathered at their crossings. Galaxies lit up along the threads like frost on a winter window. And now, after all that time, the web stretches across everything we can see. But nothing in the universe stays the same forever. The web, too, has a future. And that future is stranger and lonelier than you might expect. Right now, the universe is still expanding. It has been expanding since the moment of the Big Bang. But here is the part that changes everything. That expansion is speeding up. Dark energy, the invisible force woven into the fabric of space itself, is pushing the universe apart faster and faster with every passing moment. Scientists have measured this acceleration carefully. The evidence is clear. The universe is not just growing. It is rushing outward, and it will not stop. What does that mean for the cosmic web? Over billions of years, the great filaments will begin to thin. The threads that connect galaxy clusters will stretch. The gas that flows along them, feeding young galaxies with the raw material for new stars, will spread too thin to reach its destinations. Galaxies that are not already bound together by gravity will drift apart, carried away on the expanding tide of space. The web will not break all at once. It will simply fade, slowly and quietly, like a fire burning down to embers. The clusters themselves, the dense knots where filaments meet, and thousands of galaxies crowd together, will survive longer. Gravity is strong enough inside a cluster to hold it together, even as the rest of the universe pulls away. Our own local group of galaxies, which includes the Milky Way and the Andromeda Galaxy, is bound by gravity. In fact, Andromeda is moving toward us right now. In about 4 billion years, the two galaxies will collide and merge into one large elliptical galaxy. Astronomers sometimes call this future galaxy Milky. It will be a single, slowly spinning cloud of stars, the remnant of two great spirals folded into one. But even Milky will not last forever. Stars burn through their fuel and die. The most massive stars go first, exploding as supernovae and leaving behind neutron stars or black holes. Smaller stars like our sun burn more slowly. They will last for billions of years before swelling into red giants and then cooling into dim white dwarfs. Over trillions of years, star formation will slow. The gas that makes new stars will be used up or scattered. The galaxies that remain will grow quieter and darker, their light fading one star at a time. Scientists call this distant era the degenerate era. It is a time when most of the bright, burning stars are gone. What remains are white dwarfs, neutron stars, and black holes, drifting through the dark in the remnants of what were once grand galaxies. The cosmic web, by this point, will be almost unrecognizable. The filaments will be gone. The voids will be even emptier than they are today. The universe will be vast and cold and very, very quiet. And yet, even in that quiet, something will still be happening. Black holes will slowly gather mass, pulling in whatever drifts close. Over unimaginably long stretches of time, even black holes will fade. Physicists believe that black holes very slowly release energy through a process called Hawking radiation, named for the physicist Stephen Hawking, who first described it. Given enough time, even the largest black hole will evaporate completely, releasing its energy back into space as faint warmth. The universe will approach a state of near-perfect stillness. This is the far future that the physics of today points toward. It is not a dramatic ending. There is no explosion, no collapse, just a slow, gentle unwinding, like a long breath finally released. The web that once held 100 billion galaxies in its threads will dissolve into the dark, something peaceful in that thought. The cosmic web spent billions of years building. It gathered matter, shaped galaxies, fed stars, and made possible every world that has ever existed, including this one. It did its work without hurry, and when the time comes, it will rest the same way, slowly, without ceremony, the way all great things eventually do. The universe is always becoming something new. Even at the very end, it will simply be becoming something quieter. And yet, even as we imagine that distant quiet, we are here now, alive, awake inside the web. That is worth sitting with for a moment. The cosmic web stretches across at least 93 billion light years of observable space. That is the distance light can travel in 93 billion years. The numbers are so large they stop feeling real. But here is something that might bring them back to Earth. Every atom in your body was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen in your lungs. All of it was made inside the burning core of a star that lived and died long before our sun was born. You are not separate from the cosmic web. You are made of it. When a massive star reaches the end of its life, it explodes in a supernova, a tremendous burst of energy and light that scatters the star's material across space. That scattered material drifts through the filaments of the web, carried slowly by gravity and gas currents, until it gathers into new clouds. Those clouds collapse. New stars form. New planets coalesce around them. And on at least one of those planets, that ancient stellar material eventually became living things, became you. The calcium in your bones was forged in the heart of a dying star, then scattered across space, then gathered again across billions of years, until it ended up here. That is not a poetic idea. That is the actual sequence of events. Our sun sits in a quiet arm of the Milky Way galaxy. The Milky Way belongs to a small cluster of galaxies called the local group. The local group is being slowly pulled toward a much larger structure called the Virgo cluster, a dense gathering of more than 1,000 galaxies, and the Virgo cluster is part of our supercluster, a vast region of the web called Laniakea, which means immeasurable heaven in Hawaiian. Laniakea contains the mass of 100 million billion suns, and Laniakea itself is just one node in the larger web, one bright knot among countless others spread across the observable universe. From that distance, our entire supercluster would be nearly invisible. A faint glow among billions of others. Our galaxy, a single dim point. Our sun far too small to see. And you, reading or listening to this right now, smaller still by every measure we have. And yet you are here, conscious, curious, able to look up at the night sky and understand, at least a little, what you are looking at. That is extraordinary. The universe spent nearly 14 billion years building the conditions for that to happen. Scientists estimate there are roughly 2 trillion galaxies in the observable universe. Each galaxy holds billions of stars. Many of those stars have planets. The web shaped all of it. Its filaments funneled matter toward the places where galaxies could form. Its nodes became the great clusters where thousands of galaxies gathered. Its voids pushed outward, helping define where the threads would run. The web did not build these things one at a time. It shaped everything at once, across distances so vast that light takes billions of years to cross them. And it did so through nothing more than gravity, gas, and time. There is something deeply settling about that. We often think of ourselves as small, and we are. But small does not mean disconnected. A single thread in a vast net is still part of the net. It still carries tension. It still holds things together. Every atom in your body participates in the same gravitational story as the largest galaxy cluster. The same forces that pull superclusters toward each other also hold you to the ground. The same physics that governs the formation of filaments also governs the way water flows and the way cells divide. The universe uses the same rules everywhere. You are not an exception to the cosmos. You are an expression of it. The cosmic web is the largest known structure in the universe. It is ancient. It is vast beyond easy imagining. And it is the reason anything exists at all in the form we know it. Without the web's slow gathering of matter, there would be no galaxies, no stars, no planets, no oceans, no life. The web is not a backdrop to the story of the universe. It is the structure, that made the story possible. So when you look up at the night sky and see a single star glowing quietly in the dark, remember that star is part of a galaxy, and that galaxy is part of a filament, and that filament is part of something so large it contains everything we have ever seen or imagined. And so are you, woven in, held, part of it all. And so we rest here at the end of a long and quiet journey through the largest structure the universe has ever made. You have traveled far tonight. You have seen filaments stretching hundreds of millions of light years across the dark. You have looked into voids so wide that entire galaxy groups sit inside them like dust motes in an empty room. You have learned that dark matter, invisible and silent, holds the whole web in shape. That dark energy slowly pulls it apart. That the same physics behind a crashing ocean wave also guides the way galaxies drift along their threads. All of that is real. All of that is happening right now, while you lie still and breathe slowly and let the night settle around you. Think for a moment about where you are. You are on a small, rocky planet. It is wrapped in a thin layer of air, just thick enough to hold warmth, just clear enough to let starlight through. That planet orbits a medium-sized star, one of roughly 200 billion stars in a galaxy called the Milky Way. That galaxy is part of a small group of galaxies called the local group. The local group is part of a supercluster called Laniakea, a vast, slow-turning river of galaxies 500 million light-years wide. And Laniakea is one node among many in the cosmic web. You are not floating loose in all of that. You are woven into it. The atoms in your body were forged in the hearts of stars that lived and died long before our sun was born. Those stars formed inside galaxies. Those galaxies formed along the filaments of the web. The web itself grew from tiny ripples in the very first moments after the universe began. Everything that has ever existed traces its origin back through that chain. You are the universe, folded into a quiet, breathing shape. There is something deeply peaceful in that thought. You did not arrive here by accident, separate from the cosmos, looking in from outside. You grew out of it. You are continuous with it. The same gravity that shapes a galaxy cluster holds you gently this planet. The same atomic forces that bind stars together bind the molecules in your hands. Outside right now, if the sky is clear, the stars are doing what they have always done. They are burning slowly and steadily, each one a small sun, many of them circled by worlds we have never seen. The Milky Way is turning. It completes one full rotation roughly every 225 million years. Tonight, while you sleep, it will turn a tiny fraction of a degree. You will not feel it, but it is happening. The moon, if it is up, is pulling gently at the oceans. The tides are moving. Somewhere on a dark beach, water is sliding up over smooth stones and pulling back again. The same rhythm it has kept for billions of years. The ocean does not rush. It does not worry. It simply moves with the forces that hold it. You can do the same. The cosmic web does not need anything from you tonight. It has been here for nearly 14 billion years. It will be here long after every star we can see has burned out and gone dark. It is patient in a way that nothing else can quite match, and you are a small, warm, living part of it, resting now, breathing slowly, held by a planet that has carried life for billions of years without ever once dropping it. That is not a small thing. That is one of the most extraordinary facts in all of science. Life exists here. Conscious, wondering, sleeping life. Life that can look up at the night sky and recognize itself in what it sees. Life that can trace a line from a single breath all the way out to the edge of the observable universe and say, quietly and truly, I am part of this. So let your eyes close now. Let the weight of the day settle down into the mattress beneath you. The filaments are still there, stretching silently across the dark. The galaxies are still turning. The voids are still wide and still and full of their own quiet kind of presence. The web holds everything it has ever held, and it holds you too. You are inside the largest structure in the known universe. You are safe. You are small. You are connected to everything that has ever existed by forces older than the sun, by atoms older than the earth. Rest now. The universe is not going anywhere. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.